In the last two lectures, we identified that there are sometimes different versions of stereoisomers of molecules that have all the same bonds but pointing in different directions. While we might use common indicators of configuration that refer to the rotation of polarized light, like lowercase d and l or plus and minus, it is often useful to have a way to look at a structure without any experimental data and describe the stereochemistry. One method that we already have used is the capital D and L to talk about stereochemistry at the highest numbered stereocenter as it relates to D-glyceraldehyde. In this chapter, we will also be introducing a way to designate chirality at individual stereocenters using the special descriptor R and S. We will also take the cis and trans designation that we use for simple alkenes and generalize it so that it works for all of our alkenes, even if they are tri or tetra substituted. Let's take a different tack to see why this is important. The molecule at the right is a D-glucose. Is it dextrorotatory or levorotatory? There's no way to tell from the structure. Similarly, we can't use plus or minus from this molecule, because again, we can't tell which way it's going to rotate polarized light. We can use the D-glyceraldehyde-based system to identify the molecule, but this tells us nothing about the other stereocenters. We'd need to use a separate name, like we have for carbohydrates, for every combination of all the other stereocenters. The RS system instead allows us to label each chiral center individually and systematically for all molecules. Similarly, cis or trans work for simple alkenes and rings, but if we wanted to do a more complex system, we'd need something that would allow us to designate all alkenes like the EZ system. So we'll talk about each of these systems in this lecture. In order to give an absolute name for each configuration of atoms, we need a systematic way of ranking their priority, which is another way of saying their importance. The rules for assigning priority are called the Kahn-Ingold-Prelog rules. The main rule is pretty simple, that the higher the atomic number, the higher the priority. You can see that pretty clearly here, where bromine is more important than chlorine, which is more important than carbon, etc. Everything else is pretty much just breaking ties. One way that things could tie is if you only differ by isotopes. If atoms attached only differ as isotopes, the heavier isotope is the higher priority. Another way that you might have a tie is that if atoms attached only differ by what they're attached to. We're always going to follow this difference in the chain of highest priority atoms. For example, we'd always look at the difference of things attached to nitrogen before we worry about any differences of things attached to a carbon. We also consider double bonds as equivalent to two separate bonds to the atom in both directions. So a carbon double bound to a carbon is considered to have two carbons bound to it from that double bond, and each of those carbons are both considered to have two bonds to a carbon as well because of the double bond. Another way of putting this practically is that a vinyl group is going to have a higher priority than an isopropyl group. Draw both of these side chains out, the vinyl and the isopropyl, and make sure that makes sense to you, that vinyl is higher priority than an isopropyl. Once we can assign priority, we just need a systematic way of visualizing a stereocenter. The RS system assumes that the lowest priority group is always pointed away. The other three groups can be thought of as a steering wheel, coming off the axis of the back bond. If the numbering on the steering wheel is ascending counterclockwise, or to the left on top, the molecule is said to be sinister, or S conformation. Alternatively, if the numbering ascends clockwise, the configuration is rectus, or R. Again, this only works if the lowest priority group is pointed backwards. However, if the lowest priority group is pointed forward, you can analyze the same way, but just give the opposite configuration. R and S are for each stereocenter, so the designations are associated with an individual group. Let's walk through assigning these stereocenters and naming the molecule together. First, let's agree on a name for this molecule without a designation of chirality. Pause and identify a name for this molecule, and I'll think of a name that I like for it, and we'll see if they match. Ready? Okay, I like Charlie. Oh, you said 2-chloro-2-bromopentane? Yours is better, so let's use that. Now let's identify the priority of all the groups around the stereocenter number 2 in the name, the one with the chlorine. We have the choice between a chlorine, some carbons with stuff attached, and a hydrogen, which is not shown. The chlorine is the highest atomic number and therefore the highest priority. The hydrogen that is not shown is the lowest and conveniently already pointed back. The next highest priority is the carbon that is attached to a bromine versus the carbon that is only attached to hydrogens. We now have the priorities for all the groups and can see that the lowest priority is already pointed back. Since the numbers ascend clockwise, this is an R configuration. I erased all the numbers for the 2R stereocenter. I want you to pause and try to label the priorities for the 3 position, and then we'll go over them together. So the bromine is the most important, and then the carbon that's attached to a chlorine. And after that, the carbon that's attached to another carbon, and finally the hydrogen, which is not shown, but in this case is pointing forward. The numbers ascend going clockwise, but since the hydrogen is pointed the wrong way, we know it would be flipped if we looked at it from the other side. The center should be S. When we give these labels, we can put the R and S in parentheses before the number label. Or the R and S can be listed along with the numbers all together in the front of the name. Note that we still include the numbers later in the name as well. These designations can be useful indicators of relationships. Enantiomers will flip every one, so every R becomes S, every S becomes R, while diastereomers will invert some, but not all. Rings can have S or R designations too, but sometimes the points of difference are farther out. That's okay, we just keep following the same rules all the way around the ring. We can assign priority to groups around an alkene as well and use them to designate that alkene with the easy nomenclature system. We really only need to compare the groups on each carbon one versus the other. This is easy by comparison to the RS system. Whenever we assign easy nomenclature, we're comparing the highest priority groups on one side of the double bond to the highest priority groups on the other side of the double bond. If the highest priority groups are on opposite sides of the double bond, we say that they are E, which stands for the German word for opposed, and gegen. In simple molecules, like molecules that have only one non-hydrogen group on each side, this is the same as trans. If they are on the same side, we say that they are Z, for zusammen, meaning together in German. If the molecule is simple, this is the same as trans. Just like with RS designations, EZ designations are for a specific double bond. Here's an example. Let's start out by agreeing on the base name. You choose yours, I'll choose mine. Ready? 2-chloro-3-bromo-2-pentene? I'm glad that we agreed. Now let's give relative priority to each group attached to each carbon, starting with the left carbon. Chlorine and carbon are being compared, and chlorine is higher atomic number. We go with chlorine first, then carbon. Same thing on the other side, except bromine versus carbon. Bromine is the higher atomic number, which makes carbon lower. At this point, we just need to compare the higher priority groups. If they are on the same side of the double bond, they are Z for Z same side. If they are on opposite sides or opposite sides, then they are E. These groups are E. And the E designation can come alone at the beginning of a molecule name if there is only one bond that needs this type of labeling. Alternatively, the E label can be immediately preceded with a position, like so. In a ring, strain prevents E configurations if there are 7 or fewer carbons, but they are allowed with 8 or more carbons. Any ring with 7 or fewer carbons and an alkene is assumed Z, no label necessary. This is the big exception to EZ designation, and the rest is really just assigning priorities to groups and evaluating their relative orientations.